So let's say you're playing your favorite game. In my case, my favorite game is Mario Brothers, right? And it's a lot of fun. And there's a lot of stuff going on too, right? I can jump around, I can go on pipes, I can kill creatures, there's a lot of stuff going on here, right? So let's say that I love this game so much, I want to go ahead and develop my own game. And we're going to talk about ways to do that today. All right, so this is our presentation on finite state machines applied to game development. So, imagine yourself as a game developer and you want to recreate your favorite side-scroll game. And a side-scroll game, for example, is just like Super Mario Brothers, right? It's from the side and we move along the screen. So, how, as programmers and computer scientists, how do we go about creating this game? What are some strategies we would want to use? How do we do that? So, let's just say, for example, you want to think about developing the character in your game. Just in this case, let's think about Mario. You want to develop Mario, right? Your character like Mario. What functionality will your character need for the game, right? Well, Mario likes walking around, running, sliding, can jump, duck, could throw fireballs at creatures, could fly. And there are other functionalities, right? There's a lot of stuff to think about when developing and programming these characters. So what do we do? Like what strategy do we use? So let's just say this. I'm going to go ahead and code up. Hey, this is what I want. I want my character to jump. So this is an example of some code that I've got from the internet. And so I press B, right? I press the button B, and it sets my character to jump. Displays my character as jumping, and that's great. So great. Now my character, I have a little functionality for my character to jump. But can you spot the glitch in this code? Just take a look at it for a second. What's the glitch? And the answer is, what prevents jumping while jumping? I mean, we could call this flying as well, right? I could jump infinitely. I can jump, and I can jump again, and jump again, and jump again, right? So how do we fix this? Like, what's a solution, right? So the possible solution would be to add a conditional statement. If I'm not jumping, then I set the jumping true, and then I go ahead and I start my jumping code. So now my character jumps while it's not jumping. Okay, great. So let's say that I want to, I want to do other things. I want to add other functionality like spitting fireballs, right? So is this the best solution? Well, if I add a fireball, well then maybe there's some more bugs. It's going to involve a long line of conditional statements, and there's going to be a long list of conditions to check in those statements and a lot of possible bugs. So maybe this is a strategy we don't want to use in coding up a game. Maybe we want to use another strategy.
So earlier in the semester, we were introduced to finite state machines. And as a simple review, we had a series of states, and in between those states, we had inputs, and those inputs guided the transitions between one state and another. And if you notice, each of these states are unique, and the transitions to get to them really guide the flow of essentially the program. But how does this apply to Mario? How does this apply to our character? So essentially, we can represent our character by a series of transitions between states. The states could be several things. In this example over here, each of the states is a movement or an action for our character. Or they could perform tasks like opening a door or transitioning between worlds. Or the state could be is our character alive? Is our character dead? Several different things. Now the transitions are essentially, in this example, our interaction with the game. So they're key presses. So pressing down to duck and then releasing to go back to standing, or pressing B to jump. And if you press down while you're jumping, then you go into diving. And essentially what it does is it separates all of our characters' movements into specific states in which we can check against. So it creates a flow for our character. And why this is important is because it eliminates the need for several of those conditional statements in one specific block of code. In our previous example, that was just we had one character input and then conditionals on is this B, is this down. Now we have it more modular. This is an example in C++ of how to implement these states. We have a character, and we have an instance of that character, and its state really defines, basically what state it is in the finite state machine. So we can check against it later on. In this instance, our character is getting set to jump when we press B. And then it sets the graphics, the sprite. But this is only where it starts. This is only the beginning. Basically, what we can do is implement a push-down automaton. Because before, how did we keep track of what our character did last? Now with the PDA, we can keep track of the history of our character states, or the state of the world. So in this example to the left, Mario is jumping and shooting a fireball. Now, whenever he's done shooting the fireball, we need to return to the jumping state. And then when he lands, we can pop that jumping state into the standing state. So that history allows you to have a lot more functionality for your characters, for your games. And like I said, it's not just specific to a character. You can model every object in your environment to have this finite state machine, or PDAs, this functionality, this concept. And PDAs aren't the only thing to do either. You can go into several different branches of that idea and run with it. There are a few things to get you started. There are a lot of libraries for many different languages to implement a state machine, so you don't have to write it all from scratch. These are just two examples. Or you could write your own. And if you're doing a simple side scroller, it's probably the best way to do it, and it's the best way to learn. Actually, the new way to model a lot of this behavior in games are behavior trees, and it allows for a lot more complex modeling. I think one example is EA's Spore used behavior trees because I don't know if you've ever played that game, but there are several different states and things to keep track of within the game, where the finite state machine would be a little bit too simplistic.
Great, so these are our references. Thank you, Professor Hummel, for providing the image, and thank you, everyone, for listening. My name is Bradley Golden.
And Cody Roberts.
And this is our presentation for CS301.